So let us see lecture number 8. In previous lecture, this lecture number 7 of this module 2, we saw that we had the differential equation of the second order, and we require some algorithm or solution methods to solve those equations, because those are the nonlinear differential equations. So the various methods, as I mentioned, maybe your Runge-Kutta method, maybe your Euler method, maybe your modified Euler, that is also very important, and maybe another one, your trapezoidal methods. So to see that, let us first consider the various numerical integration methods, because here that is required to understand how we are going to utilize the Runge-Kutta method or any other methods. So there are the two type of methods for the solving this integration differential equations. One is called your explicit method. Another is called your implicit methods. That is called implicit. This in explicit method, the value of variable x, or you can say variable y, at any time t is computed from the knowledge of y from the previous time step. Means in this explicit method, your step, for example, if your variable is y, is a differentiation of y here, so this value is that you can any time step you can say k plus 1 is determined using your y k, and this is called your explicit method. So this method is easy to implement, but suffers from the numerical stability. Basically, the stability is the numerical stability implies that the error in the each step does not propagate to the future time. Means that maybe your error which are you calculating, it is keep on integrating, keep on adding, and then your system, your solution becomes absurd, and that is called numerically unstable. So this implicit methods, they are basically suffering from your stability problem. So any method that should have a different criteria, that which method you are going to use. The method can be based on your accuracy, maybe based on the stability, and method based on efficiency. Efficiency means how fast you can get and how reliable solution you are getting. So the two methods, that is the implicit method here, and another is your explicit methods. So in the explicit methods, the Euler methods, modified Euler methods, your Runge-Kutta methods are the very common. However, your implicit method, that is a trapezoidal rule of integration, is very well known, and this method, the interpolation technique is used. Here in the implicit, that's knowing this value, we try to interpolate. If you yk you are knowing, then we can here interpolate that value to get your another step. However, in these methods, we use this value to get this yk plus 1. So this is the different, and the example of implicit method is nothing but your trapezoidal rule of integration, and that is your linear interpolation is used. To see this first, the explicit method, first one, as I said, it is a Euler's method. Here, this function we want to solve. We can write this is as your y dot is equal to some function of yt. Here this y can be the vector, set of vectors, means it may be y1, y2, y3, and so on and so forth. It may be have vectors, different variables, it may be of n variables. So let us take here a simple variable x, y here, that is y dot is equal to your f yt, that is a function of y and t. We want to get the value of y, we want to solve that, we want for different value of t, we want the value y, so that we can plot and we can know the nature of this function. So here what we can do, the at any time t is equal to tk plus 1, we can write this yk plus 1, we can using the Taylor series expansion, that is your yk plus here your del yk over dt, and here some value of difference in the time, and plus 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 several other higher order terms. If you note that higher order term, what is this? This is nothing but your ft. So we can get here yn plus 1, where n is your nth, that is the iteration. Means your n is starting n is equal to 0, means at y1, means after first iteration. Y1 here will be your y naught plus your dy upon dt. This is nothing but your function fyt. And this at your value here we are just going to calculate at nth state, means here it is your f y t into h, and that h is basically the difference in the time. This is a time step, means here we are just t n plus 1 minus t n will be equal to your h. So that is your time step. This time step is also very, very important. The option that you can go for the very small time step here, then your computational time will be very high. If you are using large, then you will not get the exact function, and then your solution may become diverse and you will not get the exact function. So the choice of this h is also very, very important. Normally we go for the compromise between the smaller value as well as the higher value. So this is your Euler's method using the simple Taylor series expansion of function y that can be written here, and then we can solve, because this value we know at your naught value. So this is known to you. Using this value, previous state you are starting with the some initial guess, and then you can calculate your y1. Similarly for your y2, you are keep on getting value for the different time step. This method is not so accurate, and normally what we do, basically this method suffers from the several things. Basically the standard Euler methods gives inaccurate results due to use of its derivative at the beginning of interval, because this is at the beginning of interval, this is xn here. So this gives inaccurate result. So what is another modified Euler method has been proposed using the predictor and the corrector steps. In the predictor, this is your, let us see the modified Euler method. This is also known as the predictor and corrector method. Means at one step we predict, in second step we will correct it. Means after prediction there will be some correction, and then it is known as predictor and corrector method. So at the predictor step we calculate the value of yn plus 1 as usual. This is a yn, means we are calculating at nth iteration. So at nth iteration here this yn plus 1 means we are getting a value here, that is your previous step value, then that is a plus half y del y upon dt. This is nothing but your function here fyt, means I can write fyt, and it is n, means it is n value yn, plus here we are getting another value, this your fyn plus 1t, then multiplied by h. So this is called your predictor step. In your corrector step, what we do, we write normally this your yk plus 1, that is a corrector step here, will be equal to your yk plus half of your values, your f y t, that here it is at your step n or whatever. Here n and k slightly it is confused, means n is again the same your iteration count. So I am writing ynt plus here your f yn k plus 1 t, again here t k plus 1, and then it is your h. So this is your corrector step. So there is some first your predictor step. Here we are using this value, means this is your corrector. In the predictor I am talking again the previous one, here it is your yk plus 1. In the predictor it will be your yn plus function here yn in t into h. So this value is known to you. So this value knowing, then we can get this value. So in this corrector step, this value is known at the previous step. In this step, after your predictor, you have predicted this value. Knowing this value, you can calculate this, and after calculating this, you can calculate the corrected value of yk plus 1, and that is basically used, and then it is very, very reliable, and normally it is used. Another method, that is your Runge-Kutta method, and again it is of different order. It is even the second order Runge-Kutta method, fourth order Runge-Kutta methods, and again it depends upon the how much Taylor series expansion variables you are going to take. So the modified Euler's method is the simplest of predictor corrector methods. There are some higher order predictor and corrector methods are available, but these methods suffers from a number of limitations. They are not self-starting and needs more memory storage and requires a smaller time step than the Runge-Kutta method. So Runge-Kutta method is very popular and very widely used method. These methods, Runge-Kutta again the different kind, means second order, fourth order and so on and so forth. So Runge-Kutta methods do not require evaluation of higher order derivative, but the effect of these derivatives are included by several evaluation of the first derivatives. Depending on the order of Taylor series terms, different order of Runge-Kutta methods are obtained. So here in this transferences, I have shown here yk plus 1 is now the fourth order. You can see here it is a fourth order. If we are using second order, what we can do in the second order, I can show you this. Let's suppose your yk plus 1 means again this y can be expanded in the Taylor series expansion form, and that we can write here yk plus here again h into del y upon del t, and again here at the k plus higher order term, and that is your higher order term. I can say it is your h square upon 2 and double differentiation of f over dt square. So we are having here different order plus here again other order. So if we are taking the second order, then it is known as the second order Runge-Kutta methods, and we can write this will be equal to your yk plus your k1 variable plus k2 divided by 2, where your k1 in this case will be equal to here your nothing but your f yk into tk at that time into h, and your k2 will be your f here yk plus your k1, again we are getting at the k1 into t plus h here tk into h. So these two values are knowing this used here, and this is called your second order Runge-Kutta method. Another that is a fourth order Runge-Kutta method is very widely used, and we go for the fourth order means we are going up to the fourth order of the Taylor series expansion, and then we can write similarly after solving using basically this method is invented by Runge-Kutta, and here this yn plus 1 means nth iterations, that yn the previous iteration value plus 1 upon h6 here, earlier it was 2, so 6 here k1 plus 2k2 plus 2k3 plus k4, here you can say 1 2 3 and 2 5 and 1 6, so here divided by 6, all the terms are added, divided by 6 means this is the average of this k1 k2 k3, you can say weighted average. So the k1 is nothing but your f yn t, your k2 is your f this, because h I have taken common here, we have included h, you can see here in this case, so k1 here it was included, but here we have taken h outside, so your k1 is your simply a function yn delta tn, your k2 is a function yn plus h by 2 k1 and your tn plus h by 2, here your k3 is here h by 2 k2 now we have used, and here it is again by 2, and k4 function is hk, and here is your h value. You can see here that half we are using, and that's why it is 2 here it is used, here h completely used. So this is your fourth order Runge-Kutta method. Now let us see another method, that is a trapezoidal method. Here again just predictor and corrector methods of Euler methods, just here is explained. This predictor step we predict this, and we corrector step we correct here using this value here, you can see this yp n plus 1, and then this is other higher methods are also available, that is Adams base forth, Millman and Hamming method, etc. Another method is here normally this trapezoidal integration method, that is one example of implicit method. Here what we do, this value for any n plus nth time step, this value can be written as the yn plus h by 2, the function here at this value, and the function value at this value, here we are taking the average of this. So this is called the trapezoidal method, because here this value plus this we are taking average plus added here the value which is the function of this value. So this is called your trapezoidal method. So this is the method normally used, either Runge-Kutta, most probably Runge-Kutta method is used, and if you are using the implicit method, you can go for the trapezoidal method. Now again, question arises. Our set of equations are second order. So far here I am using the first order differential equation, that is here dy upon dt, means I have used here this dot means dy upon dt. Here I have used a function of y, that is t. But in our case, what was the equation if you remember? It is nothing but your h upon pi f, this upon dt square, plus if you are adding the damping term, here d delta upon dt, that is a speed term, here pm minus pe. So you are having a double differentiation. So what we can do, this double differentiation term, we can write the two sets of differential equation, means we can write here d delta by dt over some function here k plus delta term, and we can write here d omega by dt with another function of here, because this d by dt here d delta upon dt, this is nothing but your speed. So we can transform this double differentiation second order equation in the two single order equation, and then we can apply here using any of these methods. So in the multi-machine system we have to go for that, and we can utilize these methods for the solving the differential equation. Let us see the various factors those are influencing the transient stability of the power system. We have seen the stability constant, we saw that stability margin, we saw the various way to analyze the stability. Now let us see how we can improve, what are those factors those are affecting the transient stability. If we can know, then we can try to see that how we can mitigate, how we can reduce the instability of the system by incorporating those things. So first factor which influence the transient stability is the post-fault disturbance reactance as seen from the generator. I mean the generator from here, what will be the impedance seen by the generator. The weaker the post-disturbance system, the lower P max will be there and the P max will be lower. We saw in our previous slides that here it is your angle delta curve, that is your PE, here it is your delta. Now the post disturbance fault, we saw that once one line was tripped, then we had the less stability margin. I explained at that time. If the system is intact, then means your X is less and this P max will be higher. So your system will have more stability margin and your system will be more stable. So the post disturbance system reactance seen by generator, if it is intact, the same as the pre-fault, then it is better, even though if your X here is reduced anyhow, however it is not possible, because either you can trip the line or that system will be intact. Then if system line is tripped, your reactance will be increased, and then your this P max will be decreased and your margin will be reduced. So your post disturbance system reactance as seen from the generator, if this post disturbance system is weaker, this lower P max, and then it is influencing your post fault system. First point. Now second, the duration of fault clearing time, as we saw, that is very, very important. Means if your fault is delayed, there will be possibility that your system will land up in unstable mode, or in other words, you can see if your system fault is cleared before the critical clearing time, your margin will be, if it is very quickly cleared, means you will have more stability margin. If it is cleared at the critical clearing angle or time, then we will have the system stable. Beyond that, your system will be unstable. So the duration of fault clearing is very, very important. Means here your delta naught is this, and when you are going to clear that, at what point this delta C, the fault is clear. The longer the fault is applied, the longer rotor will accelerate. Of course, if your fault is persisting for longer duration, your machine will keep on accelerating, your delta will be very high, that will keep on increasing, and that may be difficult, that the de-escalation energy will be is not sufficient, and it will be not dissipating during the de-escalation, and your machine will keep on accelerating, and that means your system is unstable. Another factor is the inertia, that is a H. So inertia of the machine is also very important, because this higher the inertia, lower the rate of change of angle. Of course, this lower rate of change of angle, and the less kinetic energy gained during the fault. Means your here less kinetic energy gained during the fault, that you can understand by this one. This is your change in the speed, basically rate change of speed, and divided by h. So if your higher inertia is there, so the slower rate of change of angle here. You can see h is higher, your slower change, means your system will be more stable. So if your inertia of the system is very high, normally you can say system is highly stable. Fourth factor which is influencing, that is your generator internal voltage, that is your EF, determined by the excitation system. This EF, as I said, in our generation system, this is your generator. Here, this is a reactance of generator. Then we have another transformer here, and then we have two lines. That we took that example. Now, what is happening? This X at this point, this EF, excitation voltage, that is angle delta. Here V infinite angle 0. This EF can be changed by the changing the excitation of the system. This alternator. In alternator, we have the two control loops. One is controlling your real power, and that is related to your steam. Basically, if you want to increase the input power, power generated, then you have to increase the input power, and that is basically you have to open the valve of the turbine. That is going inside the turbine. Your electrical input will be increased, and thereby you will injecting more power into the system. That is called the governor loop or load frequency control loop, and we will see that one in our module number 3, load frequency control, how it is accomplished. Another control is the sensing the voltage, and it is normally going to the excitation field, that is the voltage we apply to the field winding, and that is basically directly it is your EF, that is directly proportional to the current which is flowing in the excitation circuit. So this EF can be changed, and if this EF is more, again you can say your PE, it is nothing but your EF V infinite here divided by X sine delta. So if this is more, then you are having P max more, and therefore then you will have the more stability margin. So the generator internal voltage, that is determined by excitation system and the infinite voltage system. The lower these voltages, the lower P max will be there, and therefore it will affecting your P max, means your stability. The generator loading point before the disturbance, means before disturbance, if what is your loading, means where your system is loaded at this point, loaded at this point. If it is lightly loaded, then your system is more stable. If it is highly loaded, then it again the stability will be very less, and we have to be very clear. Again, we have seen by increasing the initial loading, and I showed that one example using the equal area criteria. So loading is also very important. The higher the loading, closure of unit will be this one, which means that during acceleration it is more likely to become unstable. Another is your generator internal reactance, that is X. Here X, once machine is designed, it is very difficult to change that X, you cannot change. But while you are designing your system, while you are going to procure your generating system, you have to see what is X value. If this X is less, what happens? This X is less means we can feed more power, and this here P max, that is if X is less, what will happen? This P max will be more. Means your P max will be more if your X is less. So the generator internal reactance is also very valuable, means your lower reactance, higher peak power, and the lower your rotor angle. Means your for this P is a constant here and this is less, so your delta will be reduced, and again you are operating very close to this, you will have more margin for the fault clearing. But no doubt if you are going to reduce this, it is not possible that we can reduce very less. Why? If there will be fault at the terminal of the generator, there will be huge short circuit fault and that may damage your binding. So normally we go for the compromise between X here, and again this X is also very important while we are calculating the reactive power, because the once reactive power is directly related with this X, how much loss in that system, because I square X is the reactive power loss. So this X is basically at one hand, if it is less we are more stable, but X is more, what is happening? More reactive power and less fault current. If less, this X is less, the fault current will be more, that is not desirable. So we can see again we have to go for the compromise, that which value is suitable. Another the factor, that is the generator output during the fault, means during the fault. During the fault, if it is a dead short circuit and it is unable to feed the power, it will be huge acceleration will be there. But if it will be feeding power something to the system, then still it is less severe. So this is a function of fault location and the fault type. Which type of fault has occurred? Where is the fault? All these are the dependent. So you can say fault location. Fault type is also the factor which influence your transient stability of the system. Now, once we have seen the various factors, again to recap, we can say the post-fault reactance is one factor, the fault clearing time, second factor, inertia of the generator, third factor, internal terminal voltage as well as the infinite terminal bus voltage magnitude, here the loading prior to the disturbance, the internal reactance of generator, and the generator during the output during the fault. All these 7 factors influence. Now to improve the stability, these factors can be looked upon. These factors, how we can go for the better, that we can improve the transient stability of the system. To understand this, again we have to take a simple system. Here I have taken only one line so that we can see what is the going to be. So it is very easy basically, or you can say we have the 2 lines and the equivalent here is represented by XL. Means if you are taking the same previous example, so this XL is nothing but your XL1 parallel to your XL2. That's simple, we have represented by a single here transmission line. This is your synchronous generator, that is PM is your mechanical power feeding to this generator. This is XT prime is the internal reactance of this generator. XT is this reactance of the transformer, and this is your terminal voltage of the generator. This is your internal EF prime, just I have written. This delta, this is infinite, this V infinite, it has a magnitude V infinite, angle 0, we are taking all the quantity with reference to here 0 at this bus. So this has another, you can say theta here is theta V, and we have represented this complete. So this is your generating system, this is your transformer, this is your transmission line, or you can say including the transformer as well as transmission line is called the transmission system, and then we have the infinite bus, means we have here rest of the system. And infinite bus is as again I should recap that it is having the infinite inertia of the system, constant frequency and constant voltage, that whenever we are taking power from that bus they will be not changed, and that's why it is called infinite. To enhance the transient stability margin, we can control via P or PM. We can control here to enhance the transient stability margin, we can control via either PM, PE, or here it is a PM. So first one is the based on the power equation, that is a PE, and PE is nothing but it is the voltage here magnitude, this voltage magnitude divided by the total reactance here, this XT prime plus XT plus XL, here sine delta. Delta is angle between this bus and here at this bus, that is the internal angle. To maximize the power, means this P max, the maximum power can be increased here, this value, this is your P max, or you can say it is P max sine delta. So this max we can maximize. If this value is maximum, then we can say the system is more stable. You must always clear this. If it is more, then system is more stable. So this can be maximum if we can increase E prime, because your P max is nothing but it is your E prime. Here I have used V infinite. Here we have this xd prime plus xt plus your xl. So here we can, this can be increased by increasing this E prime. We can decrease the xl, or even though anyone, if we can decrease any of the impedance, then P max will be decreased. So these are for the P max. Or we can increase this delta, then we can increase the electrical power. That electrical power can be maximized by increasing, because here xd once machine is generated, machine is constructed, machine is installed, we cannot change this. Transformer is used, we cannot do. So xl here we can do somehow, means using some compensation techniques, we can use something, but effective xl can be reduced. Once line is constructed, it will have some here resistance and some inductance and some charging here as well. These parameters are the line constants and they cannot be changed. This is a physical parameter. But the effective value, suppose we are putting some capacitor here, then what will happen? This X is compensated with this negative reactance of this capacitance. So we can reduce this XL by using some extra apparatus, extra device, extra element in the system. So how we can do this? So this can be implemented by the techniques below. First we can use high speed excitation system. Means very effectively if we can increase this E prime. So we require the high speed excitation AVR, that is automatic voltage regulator. We can have some braking resistance. We can use some series compensation. We can use some shunt compensation. We can use some load shedding. We can use the generator tripping. We can use some HVDC link, and we can use some FACTS devices. This FACTS device we'll discuss in module number 4, and we'll see all these two in that module. So this is etc. in several other terms that can be implemented. So to control, this is basically for the electrical power that's controlling this. Another is to control the mechanical input power by fast valving technique. Means when the fault is there, the machine is accelerating. Anyhow, if the PM can be reduced during that time, effectively, very fast, because here we have taken in our analysis, this PM is the constant during that 5 to 10 seconds, because it is a mechanical device that steam is coming to your turbine. It is not possible to stop. So if you can use some fast valving techniques, then we can reduce this during that period. So the acceleration during the fault will be minimized. So the delta change again can be minimized. Once this delta change is minimized, means the change in the deviation is less. So the acceleration energy is minimized. So you require the less deceleration part, and then your system will be very, very stable. So we have to go one by one. First I said we require the high speed excitation system, means automatic voltage regulator. So this is your generator. The terminal voltage is measured, and this terminal voltage basically compared with the some terminal voltage reference value. Normally this voltage, let's suppose, is 1 per unit, or it may be 1.05 per unit, and this voltage is measured. So this is basically here this plus minus this. If there is some difference in the reference setting, this terminal voltage is not equal to your reference setting, then some error signal will be coming here, and this your excitation and the AVR system will change your EF here. So this is called this MVR loop of the system, or you can say excitation system of your alternator. So the significant improvement in the transient stability can be achieved through the rapid temporary increase in the excitation system of the generator. I am not saying that you should operate your excitation system every time higher value, because that may lead to another problem. If your excitation is every time higher, what will happen? The field current will be very, very high, and that field current will cause more loss in the system, and that may your system, your generator alternator may not operate properly, and it may be you have to cool down, means you have to have a proper cooling for that. So but for the temporary purpose, once fault has occurred, then you can increase the EF for momentarily for a few seconds. That's no problem. With this, there will be not excessive heat. But in steady state, excitation increasing every time higher value may not be possible, and that is also not advisable. So during temporary period, you can, even though this excitation can go very high value, and then you can increase the PM. And once you can increase the PM, means you will have your more stable system. So the increase of the generator field voltage during the transient disturbance has effect of increasing the internal voltage of the machine, and thus in turn increase the synchronizing power. So it will increase the synchronizing power, and therefore your system will be more stable. During a transient disturbance following a transmission line fault and the clearing of the fault by isolating the faulted element, the generator terminal voltage is low. The automatic voltage responds to this condition by increasing generator field voltage. This can be controlled by automatic voltage regulator, that is AVR. AVR regulates the generator terminal voltage by controlling the amount of current supplied to the generator field winding by the exciter. Means during this transient disturbance following a transmission line fault, and once it is cleared by isolating the faulted element, this generator terminal voltage is very less. Why? Because let's suppose this line is faulted and it is tripped. The power which is flowing here, this P, the X is more, so this voltage is normally reduced. Because you are feeding the power, this voltage due to the drop etc., this voltage is reduced. So by this we can, changing this excitation, we can increase this voltage, and then we can improve the stability of the system. You can see this PE, that is equal to your E prime V. Here this is your V, it is written here V del infinite. This is your EF. Here in this case, means EF is nothing but your E prime divided by all these three here, your XT of this, and this is your parallel of XL1, and this is your XL2. Here I have written sin delta. So that to increase the EF by AVR excitation, we can increase the PE during that time. If the PE is increased, again we can see, you can see this curve here. This was your here, and now during the fault this, and this was like this. So if you can increase this, your system was operating here, it was coming here. If you can increase this by this, then your area of here E will be reduced. So again the escalation part will be minimized, and once it is less, your system will be more stable in that sense. Now let us see the impact of AVR, and with and without AVR we can see how the system is stabilized with the help of AVR. Here in the left hand side you can see this picture here, this graph I have shown. In this case again I am assuming here, this previous case here, the fault is there, but this line is intact after the fault is cleared, means this is a three-phase bus fault, that's I have shown. In this case what is happening, that the post and the pre-fault curve is this one, this outer curve is the pre-fault and the post-fault condition, means your impedance is not changed, means lines are intact, GT is intact, and your, of course, generator is connected to the system. During fault, let's suppose we have this consideration, this fault, that is a during fault, this curve. Now you can see, if you don't have AVR and by the chance this fault is not clear before the fault clearing angle, means your machine is loaded with the PM, means your operating point is 1 during the steady state. Once fault has taken place at the bus 1, and then it is coming to this, because during the fault your PE curve is following this one. So what will happen now, this will go and it is escalating, means now you can see delta is keep on changing with the time. So it is reaching at the point 2 here, in the delta, lower is the delta curve with respect to time, this is the power with the delta curve. So you have reached here, and now your fault is clear. Once fault is cleared, now you can see from here this curve will jump to 0.5 because post-fault condition is similar to your pre-fault condition. So it will follow the PE curve of that top one. Now here this was accelerating, this was your A1, that is your accelerating area. Now this will try to go here and this is your area 2, and you will find, let's suppose your A2 here is less than your A1. So what will happen? Your system is unstable. You can understand with this what is happening from 5 to 6, again your angle is increasing, but the machine is retarding, decelerating because the PE is more than PM. Means you are taking more power than you are feeding. So what will happen? Machine will try to retard, but still it is more than synchronous speed. So it will be coming here at the 0.6, and still it is find that a lot of kinetic energy is stored and it is not released. That energy which was stored here, it is not released, means this area is less than this. So it will keep on moving, and you can say once it is crossing the 0.6, what happens after crossing? Again this machine is going to accelerate. So this happens that it was trying to, this delta was increasing, it should come back, but it is keep on moving and it is going beyond that control and your machine becomes unstable. Now let us see the impact here and your right hand side. So the effect of AVR in the right figure is to increase the field current, leading to an increase in internal EMF, that is E prime or EF we are trying to increase. Now you can see a different family of curves we have. Means all these here, these three curves, they are the family of post-fault characteristic, and here all these three are the family of faulted characteristic, means during the fault curves. And again, if you keep on increasing F, so you will have the different magnitude and different curve shape you will be getting. So increase in the EF can be accounted for by drawing a family of power angle curves for the different value of E primes. The increase in E prime has the two positive effects. Firstly, as E prime increases, the accelerating power decreases. Now you can see during this condition, means this is your, let's suppose your machine was operating at this point and this was your pre-fault condition. Now your once machine, there is a fault here, it was coming here, and in the previous case, and it was going like here, and then it was coming here. It was your complete area like A1 in this case, when it was in this case I am talking. So now what I am going to do, if we can increase the field excitation, what will happen? The here peak of this lower curve, there is a family of voltage curve here, it will be going up, and then we can have the dotted line. So what is happening? Let's suppose we have increased, then we are having this characteristic. Now what happens? Your accelerating energy, that is energy stored during the acceleration, is reduced. Now this A1 prime is less than the A prime of the previous case. So the first effect is by increasing the E prime, the accelerating power decreases and the accelerating area here is reduced slightly. Secondly, when fault is clear, now in this case, in this zone, now we will let us see, we have seen here A1 prime is reduced, means area of accelerating is reduced, and that is very important, means the energy stored is less. When fault is cleared in this zone, the system will follow a higher power angle characteristic resulting from the E prime, so that the larger decelerating area is available. So here what is happening, this larger, if you are increasing this EF, you have increased, let's suppose here, after this clearing we have increased here. What is happening? This area you can say now increase. Earlier it was only this area. So we have decelerating area is increased. So this machine will go back and it will be when area A1 it will be area A2 here. Means we are going to increase the margin and we are increasing the stability margin of the system. So in this example, the decelerating area, that is a 4, 5, 6, 6 prime, is equal to the decelerating 1, 2, 3 here in this case. So by increasing this AVR using this more excitation during the fault and the post fault, your system is stabilized. Once system is again stable, stabilized, then again you can operate to its normal value. There will be no problem. So with the help of AVR, automatic voltage regulator, we can improve the stability of the system. Now another impact, let us see the breaker resistance. Means here there is a breaker which is having some resistance. So the dynamic braking used concept of applying an artificial electrical load during a transient disturbance to increase the electrical power output of generator, thereby reduce the rotor acceleration. What we are going to do, if there is some fault, in the previous case we saw that if it is a voltage fault at the bus, what is happening, it is suddenly, if you see here, your system is operating like this, here your PM, it is suddenly coming to 0 and then it is going and then it is accelerating like this. So what is happening, it is suddenly 0. So anyhow, if we can, this P that is can be increased, means we want some P value, means we can do something here up by using some dynamic resistance, putting some resistance in the circuit using the help of the breaker here. With some breaker here, dynamic resistance is used. What will happen, this will deliver some electrical power and thereby this area is now reduced here. It is less than previous area, here it was this area. So this braking resistor is basically dynamically added to the system, and once the fault is clear, then we can remove this resistance. So the shunt resistor is connected at the generator terminal. It is switched in following a fault to reduce the accelerating power of the generator. Means now accelerating power of the generator means the electrical power which is taken out is increased, so that we have the less accelerating power, and remove the kinetic energy gained during the fault. From above figure, means this figure just I am talking, a braking resistor is switched in at an angle of fault clearing. The admittance Y11 and Y12 at this point can be derived here. In total, just I am not going in the mathematical complexity, it is better that we can see the effect of this. Means simply what we are doing, the electrical power we are taking from here, and thereby we are reducing the accelerating energy, and that means your delta increase is minimized during the fault condition. So we can here at this bus we can form the Y11 and Y12 here, and we can get what will be the seen impedance at this bus, and then the electrical power of system with the braking resistance can be calculated by this equation, where A will be this. It can be mathematically solved, and we should not go in the complex mathematical derivations. Now here you can see with the braking resistance and the without braking resistance. With this curve I think is more clear. This is your PM where the machine is loaded. This was your pre-fault system. This is your pre-fault system, and here your point is your operating point. Now once fault has occurred, during the fault it is suddenly here it is coming to the 0. This is from B to C, means without braking resistance the accelerating area ABCDI here, because here the post fault without the braking resistance, this is your post fault. So this area that is more than the decelerating area, that is your IJ. Where is I? This I, H, J and G, means this area. So here your this area basically DCDI, this area here, this area is your less than this area, and this area is more than this area, and unstable case. But if you are using the braking resistance here, what is happening, your post fault with the braking, you have increased your, this is a parallel, you have increased some more resistive power. It is not X, it is the resistance power that is added here directly, this real power. This is a resistance, you must know this is resistance, so the only this real power P, and this P is added together on this curve, means your here this is your P delta curve. If you are adding some resistor at this, so this curve will be like this, it will be added this P that is going in the resistor. So this curve is lifted here, and then you can see the accelerating area ABCK will be equal to the decelerating area KEFG. Here this area we're getting, and then we have more margin. You can see here this is a margin just we are having. So your system becomes more stable. So this is, you can say, the impact of your breaking resistance. Now see your series capacitor. Means we can, using series capacitor, we can also improve the stability of the system, and we can also see that we can improve the stability margin of the system. Means your system will be more stable if you are using series capacitor, or you can say series compensated lines. The series inductive reactances of transmission line networks are primarily determinants of stability limit, because we have added this X. The reduction of reactances of various elements of a transmission network improves the transient stability by increasing the post-fault synchronizing power transfer. The series capacitor is one method of reducing the network reactance. I said, now if you are using this XC, here this parallel impedance, your XL parallel to your XL2, now you are using here plus, here it is minus of this line, plus your XT here plus your XD prime. So this is your total X. So what is happening? This minus XC is reducing your X. So we can see with this here, if you are X here, I think it's wrong. Here this is the with XC you are getting more, because your XC is reduced, and without XC here you are getting less P max. Means P max is changed. So here this is your without XC, and with XC you can see your P max is increased, and thus your system is going to be more stable. A series capacitor directly offset the line series reactance. Directly offset means directly reduced here. X is simply it is reduced here. The maximum power transfer capability of transmission line may be significantly increased by the use of series capacitors banks. This directly translates into the enhancement of the transient stability depending on the facilities provided by bypass the capacitor during the faults, and for the reinsertion after fault clearing. Let us consider the power equation without series capacitor and the with series capacitor. Without series capacitor, here there is no minus XC, but here we have used XC component as well. So what is happening now? The P here is the with XC is this one, and without here this is your XC. To understand this, with C, without C, you can see this is your pre-fault curve, this curve, outer curve. Your post curve, here we have the two post fault with your series capacitor, and here post fault with the C short circuited, means without capacitor. Means your capacitor is here. You can have some switch here, you can start it by closing, or you can open, then it will be inserted into the circuit, and this is your during fault condition. Now we can say without, here means without capacitor, what is your condition? Here this is your system after fault is coming. Once your fault is cleared, this is going at this point, and then it is now going to oscillate here. So now you can see your area here, this area, your ABCM area, this area here, that is more than this area. That area, that is a decelerating area, it is your MDK, this area is less, means your system is less stable. Means here if the area is less, means it is not stable at all. But there is a possibility, if cleared your fault this, then you will have the less margin. If you are using the series, and again this is after the fault, one you should mind. During the fault, if you are putting this, what will happen? This may create another problem. So here this value, if you are putting the C, what will happen? This will be another curve here, and again this may be useful in that period. So if you are using the capacitor, what is happening? Your operating point at this. Now after this here, it is going like E point. So this is your area. Now it is coming here, and you will find if this area here, this shaded area A1 now will be equal to your A2, this area 2 here, your system will be again going back and system will be stable. And now you can see you have this much margin. It's a huge margin you are having. This is your margin and your system is very, very stable. Means you have a more stable region. Even though your fault is cleared after delta A, still your system is stable. So you can see the series capacitance that can improve the transient stability of the system, or in other words you can say it will increase the transient stability margin of the system. Means it will be more stable. Another, let us see the impact of your fast valving of your PM. That's we are going to, till now just we are looking at the PE. Now here we are going to see the PM. Cut. So let us see the impact of the fast valving action, in which previous 3 slides and 3 cases for improving the transient stability, we saw that we can improve the transient stability by EF, or you can say E prime, by your changing your XC, means you can put this XC in the system, and we can improve the transient stability of the system. Now it is on the another side, that is your PM, that we can change the mechanical output of the system during the fault and the post fault. What is happening, if it can be basically done by the rapid closing and opening of the steam valves in a prescribed manner to reduce the generation oscillating power following the recognition of a severe transmission line fault. Let us see this here, this curve here. This is the left hand side is a diagram when there is no fast valving action is there, and you can see this area A1 is more than your area 2 and your system is unstable. Already I explained this when I was explaining your EF system, means with the AVR action. Now in this your right hand side you can see when the fault occurs here, means your system operating at point 1, and the fault occurs means your point is coming here, and this is your it is following your PE this. Now again, if you can have a very fast action, so you can change at this point when fault has occurred, you can reduce this PM as well here. For example, you can reduce the PM. So what will happen, your this oscillating area will be reduced, but this time is very, very fast and it may not be possible, let's suppose. But even though your fault is cleared at this point, then during that period again we can reduce this PM. Then what will happen, we are increasing here the de-oscillating area, and here increasing your de-oscillating area A2, and we are decreasing your oscillating area. So what is happening, we are improving the stability of the system. Means here again it can be, you can have more margin, means you can have, even though system cleared before and your system will be stable, means you will have more margin here. So you can see the here delta, which was keep on increasing beyond this 0.6, but here at this point your delta is going back, and we can say here your delta is stable. So this is your delta with the reference to the time. So we can see with the help of this fast acting valve, means rapid closing and opening of the steam valves, we can again improve the transient stability of the system. So we have seen in this lecture that how we can improve the transient stability, what are the various methods to improve, means we can solve the differential equations. First we discuss about the various methods, including your Euler's method, modified Euler's method, Runge-Kutta methods, and then of course the trapezoidal methods, and then we saw the various way to improve the transient stability. Along with, we also saw the various factors those are influencing the transient stability of the system. Thank you.